Okay, so in the last lecture we discussed about the various properties of detectors, right? And in this class, as you can see, what you can see on the board over here is a basic block diagram for counting system, entire system, not just the detector, for energy spectroscopy only, not timing, only energy spectroscopy. So where do we start with? We start from here with source, right? So the source emits radiation. Possibility of detection is there if we introduce a detector, appropriate detector. Now, as a result of the detector, what will happen? Signal after interaction of the radiation with the detector material, active medium of the detector material, what will happen? Electronic signal will be produced, right? Now, we will play with the extraction of information from that signal, right? So the main job of the detector is to produce signal, and now the signal we have to extract, make it usable for us, so that we can extract the information about the radiation particle. Okay, good. So how do we start? The first thing to know is that when the signal exits the detector, I have shown the representative diagram over here. Okay. The first thing is, this amplitude is very small, say of the order of millivolt. Number one. Number two, you see, the height is small and the extension or the tail part of the pulse or the signal pulse, or you can say this is the rising part and this is the falling part. So falling time, okay, tail part of the pulse is quite large. Points to note. Another point to note is the impedance is also very high at the end of the detector. These are the points to note. So detector accepts radiation, produces energy pulse. This is the pulse, but the pulse has very less amplitude. The tail part is quite long. Of course, this is an asymmetrical pulse. Now the next part is what? What should we do? Come on, amplify the pulse so that we can use it. Okay. At least voltage order, so 1000 times magnification is required, right? That means millivolt to volt. We have to amplify it. That means I have to increase the y-axis of this pulse. But remember this part, this width of the pulse. So and also the very fact that this output impedance is very large. So the next component after the detector is not the amplification part, but rather an impedance matching device, which is the preamplifier. What does it do? It basically matches the impedance between the output of the detector and the next very important component where the main amplification is done, that is amplifier. Okay, so impedance matching device. Along with this word, this preamplifier in fact also slightly amplifies the pulse and reduces noise. So here you can see the detector pulse, here it is little bit more, y-axis is little bit more. So this is the preamplifier. Again you see, it is similar. There is nothing happening to this tail part of the pulse. Okay, and this has already matched the impedance between the detector and the amplifier. Okay. Now, in the next part, so the signal is traveling like this. Okay. Now we are in the pre-amplifier part. Now after that, this signal goes to the amplifier component. Now you must remember that when the signal is first generated, along with this signal, this is an electronic device. All of these are electronic devices. So in an electronic devices, due to many reasons, soldering, joints and many other reasons, always an electronic noise is there. So when the signal is there, signal is produced, some noise is attached with it and it also travels like on the back. So this is the signal moving on and the noise on, like so together they are traveling. What we have to do, get rid of the noise component. Okay. Now the first component where this is done is the preamplifier. It slightly reduces the noise, but major noise reduction is done over in this part, amplifier and the single channel analyzer. Now let's see what the amplifier does. As the name suggests, it amplifies. That means the y-axis amplifies more than 1000 times. So here, if the voltage is of the order of millivolt, the amplitude, for the case of amplifier, it will be of the order of volt or so. This is the amplifier pulse. Now look at the pulse. Number one. See, in these two cases, it was asymmetric. The tail pulse was very large. Right? Now here, what happens is that along with the signal amplification, basically which enhances the pulse, this also shapes the pulse. That means the tail part is now gone. It is a symmetric pulse. Now what's the advantage? The advantage is that this will prevent an overlap of signals. So what can happen is that some pulse is there, okay, some radiation interacts with the detector, as a result of this we have pulse, and immediately after some time here another signal is there. So what will happen is this, we will observe something like this. So you see, this is the overlap pulse, and as a result the entire energy information carried by the signal is distorted. It doesn't matches that of the original particles, radiation. Okay, so we must avoid the pulse overlap, and shaping is a very proper way to avoid this pulse overlap. And because of this, preventing overlapping of pulse, okay, what will happen is that the energy resolution will improve. Overall energy resolution due to the counting system. Okay, remember what I am saying. Previously I was talking about energy resolution as a property of the detector, but all these components have a noise in itself, right? They can affect the signal width as well, and because of this thing, that means preventing of overlap of pulses, energy resolution will be improving. So even if you choose a detector which has got very good energy resolution, if you have not so good components, then the pulse width will be very large, and you will, what will you observe? You will observe the overall effect. So overall effect will be very bad energy resolution pulse, even though your detector has got good energy resolution. Understand? So we have to keep all these things in mind. Okay, let's continue. So amplifier, not only it amplifies the signal, that means enhances the signal, but also it provides pulse shaping, thereby preventing overlaps of pulse and improving the energy resolution. Now you see, this pulse shaping, this also reduces noise, and together enhancing signal and reducing noise, this causes the signal to noise ratio to improve. This is very important. So using very good amplifier, not only we are able to improve energy resolution, in fact we are able to improve the signal to noise ratio as well. Keep this in mind. So just having a good detector is not good enough. Remember, I talked about the properties of energy resolution, efficiency, peak to total ratio, but that was only for the detector. And now I am talking about the entire system. Okay. Now after that, we have got the discriminator. It's time to discriminate the pulses. Why, you may ask? The reason is simple. Even after doing so many techniques, even after using so many techniques, noise will be there. You cannot reduce it. So now what we are going to do is we are going to use another technique to reject noise and also to reject any more unwanted signals which will be there. And what I am going to do this time is I am going to consider two discriminators. What does a discriminator do? Very simple. Suppose this is the voltage axis. A discriminator, if I use this single discriminator, what I put a condition that accept only the pulses which are above this certain threshold energy level E and reject everything which is below. Okay, so if I put a condition like this and if I have a signal pulse like this, will it be accepted? No, it will not be. What about this one? Will it be accepted? Of course it will be. So this will be accepted. This is the result of using a single discriminator. Right? Now I am going to move forward and use two discriminators. Look over here. One discriminator E with the condition that accept all the pulses which are above. And another discriminator delta E which is fixed with respect to E. And this will accept only the pulses which are below the delta E. And then I will put the two in coincidence. So the result will be, I will be accepting only the pulses in this zone. So out of these three pulses, this will not be accepted. This will not be accepted even though this is above, this is below. Only this one which is in between will be accepted. Okay? So in this way I will be able to scan the entire spectrum. How? You might ask. So let's draw this. So, suppose we are again going to consider our classic 137 cesium source where primary gamma ray is 662 keV. Right? Now, it will have a spectrum like this. Fine. And this is around 662 keV. Okay? 137 cesium. Good. But when we will do the experiment to verify this is what we will do. We will be verifying the spectrum in the lab using the instrument, right? So what we will do is, we will start from here, very low. We will put the E. Now the detector that we have, it doesn't know kV energy. What it knows is just volt. So we will start with E equal to 0 volt and delta E will be fixed. Say delta E is equal to 0.2 volts or 0.1 volt. Say we will start with E is equal to 0 volt. Then what does this mean? I am choosing an energy bin like this. Remember, volt here means energy actually. So then slowly I will be shifting this window. And slowly and so forth, right? So after some time, I will put the energy bin over here and delta E will be fixed. After some time, energy bin will be here. After some time, energy bin will be here. So I will be moving forward like this. So this is the way I am going to scan the entire spectrum. And this is how, using the single channel analyzer, I am going to record the entire spectrum. Now each time when I am doing this scanning for the particular window, the thing is happening. we are only detecting the pulses, recording the pulses which are in between the window and not anything outside. This is why I said the SCA, it records on, it rejects not only the noise but also any unwanted signal. When I am recording this particular zone, everything outside it is unwanted. Only this part here is the wanted part. Okay? And next time I change this one then becomes unwanted. And this is the way how I am going to record the entire spectrum. So the single channel analyzer is basically using two discriminators at the same time and then using the coincidence technique, right? And then thereby using the window and record the entire spectrum. Any questions? I will be able to record this spectrum. Otherwise, how are you going to record it? You see, as a result of this is counts, okay? And this is voltage, discriminated voltage. Discriminated voltage. Basically, this is the E in terms of V. So, when you do the measurement, say time is equal for all the measurements. Say time is 30 seconds. Okay, so when you do the measurement over there, you get this. When you do the measurement, you get this point. When you do the measurement, you get this point. So you will get all the points over here, and then you will join them and get the spectrum. Okay. Otherwise, if you don't fix the time, it doesn't make sense. Nah? Then if you don't fix the time, then this means particular energy channel you are giving more importance compared to others. Okay, so you must fix the time during this entire measurement and then slowly take the data. Okay, now there are certain also interesting points over here. Say for example, one is the amplifier gain. There are 2 points to be noted. One is amplifier gain and another is amplifier pulse shaping time. Now amplifier gain means what? Suppose this spectrum, this was say observed as 3 volt. Now I can change the gain of the amplifier, and after some time what you will observe, if you do the measurement for all 30 seconds, here it is 3 volts. See, the overall area will be conserved, will be equal, but the peak changes, and this is the result of the gain in the amplifier. You change the gain, the entire stuff changes, but overall area will remain fixed since the timing for the 2 measurements is the same. You can check this over here in this module. Next, pulse shaping time. Unfortunately, it is not there, but it is basically related to the pulse shaping, the width. So if you increase the pulse shaping, this thing, the shape will decrease. So if you have more pulse shaping in the module, the FWHM will be better. But again, most pulse shaping means you have more dead time, right? Because you are doing analysis for a lot of time for a given pulse, and the entire system is dead. So from the detection of a system, you see, so in the detector, basically, the moment a particle appears and it is detected in all the electronic components, so something appears and then it is processed in the electronic components, during this processing the detector is dead. It doesn't record information about the particles incoming. Of course they will be incoming, but it will not tell you. Why? Because I have already, the detector will say, come on, I have already accepted one valid particle, I have given you a valid pulse, and the system is now processing it. So unless the system completely processes, it will not record. This is the way the system works. Okay. So if you have a very large pulse shaping time, it takes a large time. So in a way, you are losing a lot of data. You understand? Large data time, in fact. So doing experiment means compromising the stuff, which is important. You have to understand. Again, if you put a source very close to the detector, what will happen? If you put a source very close to the detector, count rate will be high. I mean, in 1 second you will get lots of pulses. Do you think it's a good idea, or there is something bad can happen? The thing is that there is a time for which the detector window opens for detecting the signal. Now in this time, if you put the source very close to it, in that time 2 or more, same 137 cesium I am using, 2 or more gamma rays will enter. So what will the detector detect? If 2 gamma rays enter, the detector will say, I have detected a single pulse of value 662 into 2. So this means you have to be careful. Don't put the source very close to the detector. Source of very high strength. Otherwise, you will have what? Summing. This is known as summing effect. You will have summed up signals more and more. So what you will observe in the spectrum, if this is the 137 cesium, okay, this is 662, okay. Now if you just have only 137 cesium source and that of very high source strength, then what you will observe is the twice value is over here. What you will observe, this will not go to 0. Then again at some other value you will observe this. This is due to 2 into 662 kV. That means 2 gamma is being entered. And if the source strength is even more, then this will again not go to 0. You will have again this 3 gamma rays entering. So this is the effect, summing effect. Okay? So you have to be careful with this. একই সময়ের ভেতরে যদি আমরা দুটো তিনটে জিনিস এন্টার করে the same time frame, if 3 gamma rays enter, the detector doesn't know that 3 gamma rays have entered. It will just open the window, it will observe how much signal is there, how much charge is being collected. Now, if 3 gamma rays enter, the charge will be proportional to 3 times, and it will say, I have detected an energy equal to 3 into 662 kV, and not 3 gamma rays, because detector doesn't know how to differentiate. Okay? To get rid of the problem, there are 2 ways. Number 1, put the source a little bit far, or use a segmented type of detector. I mean, when the gamma rays are entering the detector, if you make a detector granular, I mean more and more smaller components, so that the possibility of the gamma ray entering a single detector decreases. If you have multiple smaller shaped detectors, then at a time 2 gamma rays will enter 2 separate detectors, and you will get a single event. You will get this signal from 2 separate detectors. Okay, and no such summing effect will be observed in a single detector. Amplified gain ka bola na. This peak you can change, and that is done through the amplifier. Amplifier basically it changes the entire signal. you have to do this and see for yourself in the lab. Follow? Efficiency, different detectors will have different energy resolution, different efficiency and all that. If two gamma rays enter the same detector, you will observe this effect. You have to keep the source strength low. You do the experiment in the lab, check for yourself whether you observe this or not. Our in lab here in universities, the source is so weak that if you just put the source above the detector, you will never observe these things. You check for yourself, you will not observe these things.